Today we're going to talk about solving systems of equations. Now there's three scenarios for solutions to systems of equations. Either the system has one unique solution, the system has infinitely many solutions, this is sometimes called underdetermined, or the system could have no solutions. This is often called overdetermined or inconsistent. Now, regardless of which scenario you fall into, the method of solving these systems is the same in each case. So we're going to start with Gaussian elimination, and this is a fancy name that they gave to steps that you may have even taken in your algebra class in high school. So let's start with a simple system of equations, just two equations and two unknowns. One way to solve this system is to subtract the second equation from the first. So we're actually performing subtraction on the left hand and the right hand sides of the equation. So the first equation, and I'm subtracting the left hand side of the second equation. And then I take the right hand sides and take the first equation and subtract the second equation. And what I'm left with, x1 minus x1, so I'm not left with any x1 terms. And then 2x2 minus x2 leaves me with just an x2 term on the left. And then, of course, 11 minus 6 is 5 on the right. And so I'm left with this new equation, x2 equals 5. Much simpler. And in fact, gives me part of the solution to this system. Now, in case it didn't dawn on you, the reason why we can do that is because this is an equation, right? It's an equality. So I'm doing the same thing to the left and right hand sides of this first equation. I'm subtracting equal amounts. So that's what this equation tells me, that these two amounts, 6 and x1 plus x2, are equal. So I can subtract the same thing from both sides of an equation. Okay, so if I pair this much simpler equation, x2 equals 5, with one of the original equations, then I have a system whose solution becomes pretty clear just through substitution. So if x2 is equal to 5, then using either one of these, obviously x1 must be equal to 1. This final process of substitution is often called back substitution, because we're taking one known variable and substituting it back into the equations. Okay, so for any system of equations, there are three operations which will not change the solution set. We just looked at one of them. And let's take our simple system from this example and look at these three operations individually. So the first one that we can do is we can interchange the order of the equations. I'd hope you agree that the first set of solutions, or the set of solutions to this system of equations, is the same as that to the one where the equations are written in the reverse order. We can also multiply both sides of one equation by a constant, right? As long as I do the same thing to both sides of an equation, I'm okay. So, for example, the second equation doesn't change if we multiply through by 2. So here, the second equation, x1 plus x2 equals 6, I can change that to be 2x1 plus 2x2 equals 12. And I haven't changed the solution set at all. The last thing we can do is what we started with. We can replace one equation by a combination of itself plus a multiple of another equation. Because if I form a multiple of one equation, I haven't really changed anything. And if I add these two equations together, even after I've multiplied one by a multiple, if I add them together, I haven't changed anything either because I've done the same thing to both sides. So like we did previously when we took equation 2 and we subtracted equation 1, what we did was add a multiple of equation 1, right? The multiple was negative 1. And so this is why we call it Gaussian elimination, because we're going to go through and eliminate variables from equations until we get to a place where we have a very simple equation remaining. And so we're going to use those row operations to transform our systems into those that are triangular. And so a triangular system is one that can be solved by back substitution. Take this one here, for example, which is 3 equations and 3 unknowns. When we are done with it, we hope that it's going to look like this, where we have one of our unknowns completely solved for, and then we can do this process of back substitution to solve for the other variables one by one. So let's see an example of this. Here we have a system of equations with 3 equations and 3 unknowns. And we want to transform it into a triangular system. So if you can think of this triangle here that I'm drawing with the mouse, those are the values that I want to keep. And I want to eliminate all the other values in here. So we'll start on the left-hand side, and I want to eliminate the variable x1 from the bottom 2 equations. And I can do that by replacing the second equation with the second equation minus the first. So I'm going to subtract the first equation from the second equation. And I'm going to do the same thing with the third equation. Subtract the first. So once I do that, looking just at the second equation, I have x1 minus x1. That's 0. I have negative 2x2 minus x2. That's negative 3x2. And then I have 2x3 minus x3, leaving me with just 1x3. And then I also have to do that to the right-hand side. So I have 4 minus 1 is 3. So this equation here is our new equation 2. So I've replaced equation 2 with equation 2 minus equation 1. And then I do the same thing with equation 3. x1 minus x1 is 0. 2x2 minus x2 is just x2. And minus x3 minus x3 is minus 2x3. And 2 minus 1 is 1. So we're getting closer to a triangular system. Now what I need to do is use this term to eliminate the x2 from the last equation. So when I go to do that, I have to keep in mind the 3 possible row operations I can do. Certainly, I'm allowed to multiply this second equation by 1/3 and then add together these 2 equations. If I want to not use fractions, if I want to be lazy, which I usually do, I can swap the second and third equations. And then I'd be eliminating the negative 3x2, which would be easier to do. So by swapping these 2 equations, you can see what I mean. Eliminating this negative 3x2 is much easier, because now I just have to add 3 times equation 2 to the bottom equation. So this is just that same system rewritten. I've already swapped these equations. And so now we're going to replace equation 3 with equation 3 plus 3 times equation 2. So I have negative 3 plus 3 times x2. So these terms will cancel out. And then I have x3 minus 2 times 3 is 6. So x3 minus 6 times x3. So that's negative 5x3. And then I have 3 plus 3 times 1, which is 6. And so now my system of equations is in triangular form. And you can already see that I'll be able to solve this by back substitution. All I have to do is solve for x3 by dividing both sides by negative 5, and then I can plug that value into the second equation to solve for x2, and then I can plug both of those values into the first equation to solve for x1. And that's how back substitution works. So what we just did is exactly the procedure that we have for Gaussian elimination. So we're going to now formalize that in its matrix format. And what we're going to use is called the augmented matrix. And this is going to contain all of the numerical information from a system of equations. So all of the coefficients and the right-hand side values. All of the things that are numbers, not unknowns. So if our system is written like the one here, where the x variables are the unknowns, then we're going to take the coefficient numbers and put them in a coefficient matrix. And then we're going to draw this vertical line and also let that matrix contain the right-hand side values. So again, all the numbers that we see in a system of equations is going to be written in our augmented matrix. And so the augmented matrix, because it contains all of that information, we can perform those three operations on the rows of the augmented matrix. So let's formalize those operations now. We can swap two rows of the augmented matrix. That is the same as interchanging the equations in a system. We can replace one of the rows by a non-zero multiple of itself. That's the same as multiplying an equation by a constant. Again, because we are containing both the left and the right-hand side values in here. So when I multiply something by a constant, I'm going to multiply all the coefficients by that constant and also the right-hand side. I can also replace a row by a linear combination of itself plus a multiple of a different row. So this is the same as multiplying one equation by a number and then adding it subsequently to another equation. And so our ultimate goal is to transform that augmented matrix into something that has an upper triangular form, at least on the left part. And this will allow me to solve it using back substitution. So I'm going to take my augmented matrix, I'm going to transform it into one that is upper triangular on the left-hand portion of it. And then if I want, I can convert this back to a system of equations and use back substitution to solve. So the key to this process at each step is to focus on one position. We're going to call this the pivot position, or simply call it the pivot. And we're going to try to eliminate all terms below this position using three row operations. So in our augmented matrix, we'll start always at the top left-hand corner. And this is exactly what we did when we had the system of equations written out previously. We kept the variable in the first equation and then used it to eliminate that same variable in the subsequent equations. So once we identify this pivot, our goal is to eliminate the numbers below that are circled using this row with the pivot. So here we'd replace row 2 by the combination of row 2 minus row 1. And you'll notice this is the same exact system that we did before. So we're watching these same operations happen now in an augmented matrix. So we're going to use a shorthand for this, where we're going to say row 2, R2, that's row 2 prime. So the new row 2 is going to be equal to row 2 minus row 1. So the new row 2 is going to be the current row 2 minus row 1. So this is the augmented matrix that we started with, and then I'm always going to use a long arrow with whatever operation we're performing written on top of it, and then the new augmented matrix that results. So I take this second row and I subtract the first. So I have 1 minus 1 is 0. Minus 2 minus 1 is minus 3. 2 minus 1 is 1. And 4 minus 1 is 3. And so this is my new row 2. And now I want to eliminate the next circled number. And by eliminate, again, I just mean change to 0. So again, I'm going to use the pivot element, and I'm just going to create a new row 3 where I subtract row 1 from row 3. So I have 1 minus 1 is 0, 2 minus 1 is 1, minus 1 minus 1 is minus 2, and 2 minus 1 is 1. And so I've used this pivot to eliminate the circled elements below it. So now I have to identify the new pivot. So the next pivot, all we do is we move on to the next row in the next column and pick our pivot element. Now this pivot can never be 0. If it is 0, I have to swap rows in order to bring a non-zero number into that position. And if this entire row is zeros, then there is no pivot here, and I have to move on to the next row. Okay, so here we have our next pivot. So the pivot is negative 3. And again, looking into the future, I can either, because I want to eliminate the circled element below the pivot, I can either add 1/3 of row 2 to row 3, or I can be lazy and interchange row 2 and row 3 so that my pivot element is 1, and then I don't have to use fractions in that next calculation. So it's important to know that either way you proceed will lead you to the same solution. There's nothing wrong with doing it either way. Just, I like to be lazy. So we're going to go ahead and switch those rows. And so now, like I said, the pivot element changes to 1. And now I can just do row 3 and add 3 times row 2. So minus 3 plus 3 times 1 is 0. That goes there. And then I have 1 plus negative 2 times 3. So that's 1 minus 6. It's minus 5. Goes there. And then 3 plus 1 times 3 is 6. And so now I'm done. This is my final pivot element here in the corner. Even though we don't have elements below it to eliminate, we still call it a pivot. And so I have 1, 2, 3 pivot elements, and I've created an upper triangular matrix. And so when we've reached all these pivots, we call this augmented matrix row echelon form. And that is what's reached at the end of Gaussian elimination. So row echelon form amounts to an upper triangular system. And all that means is that the entries below the pivots are equal to 0. Or you can say the left part of the augmented matrix is upper triangular. And so if we transform that back into equation form, we can clearly see that we can solve it by back substitution to get what are the same answers that we got when we perform these operations on the equations themselves. So this system right here is exactly what comes out of here, right? I have my coefficient matrix times my vector of unknowns is equal to my right hand side. So the 116 is the right hand side, 116, or negative. Or, well, 6, because I've already moved the negative over. Okay, so as a recap of what we just did, we start by identifying the first pivot element. This should be located in the first row. If it's 0, then we interchange rows so that it's not 0. And then we eliminate all elements below the pivot using that combination row operation. Then we determine the next pivot and go back to step 2. So at each step we find the pivot, we eliminate everything below that pivot using the pivot. Again, only non-zero numbers are allowed to be pivots. if you find that the coefficient in a pivot position is 0, then we have to interchange the rows to find a non-zero pivot. If this is not possible, if everything in that row or in that column is a 0, then we continue on to the next possible column where we can find a pivot position. And then when the entries below all of the pivots are equal to 0, the process stops. And we say the augmented matrix is in row echelon form. And this means that we have a triangular system of equations that can be solved using back substitution. So there's a connection between the pivots in Gaussian elimination and the rank of a matrix. The rank of a matrix can be defined as the number of pivot elements used in Gaussian elimination. We say a matrix has full row rank if there is a pivot in every row. A matrix is full column rank if there is a pivot in every column. And a matrix is full rank if it is either full row rank or full column rank. So either one of these conditions is enough to say that a matrix is full rank. And so if that matrix is square, then it has an inverse, because a square matrix with full rank has an inverse. So another way to say this is that a square matrix with a pivot in every row has an inverse. So here's a place where you can check your understanding. Try to use Gaussian elimination to solve the following system of equations. So you'll notice when you write out the augmented system here, the first pivot element that you would choose here is 0. 0 times x1. So since 0 can never be a pivot, I can't use 0 to eliminate anything. I have to swap rows and make sure that there is a non-zero element to start with. So that should get you started. Try to go through the process of Gaussian elimination to solve this system, and then tell me if the coefficient matrix is full rank. So you'll have to pause the slides here. And here is the solution. You should come out with the solution of x1 is equal to 0, x2 is equal to 1, and x3 is equal to 2. This is how we'd write this in matrix form. And yes, the coefficient matrix is full rank because it does have a pivot element in every row. Or you could say it has a pivot element in every column. These two things are equivalent. So this is all we're going to talk about today. When we come back next time, we're going to talk about Gauss-Jordan elimination, which is an extension of Gaussian elimination, but takes the process a little further.